Hello and welcome to Advent of Code, Day 5. So this is called print queue. So let's look at this problem. So satisfied with their search on Ceres, the squadron of scholars suggests subsequently scanning the stationary stacks of sub-basement 17. The North Pole printing department is busier than ever that it is close to Christmas. While the historians continue their search of this historically significant facility, an elf operating a very familiar printer beacons you over. The elf must recognize you, because they waste no time explaining that the new Sleigh Lounge safety manual updates won't print correctly. Failure to update the safety manuals would be dire indeed, so you offer your services. Safety protocols clearly indicate that new pages for the safety manuals must be printed in a very specific order. The notation X pipe I means that if both page number X and page number Y are to be produced as part of an update, page number X must be printed at some point before page number Y. The elf has for you both the page ordering rules and the page to produce in each update. But you can't figure out whether each update has the pages in the right order. So if we look at this, we have two sections. So the first section specifies the page ordering rules, one per line, and the first rule 47 pipe 53 means that if an update includes both page number 47 and page number 53, then page number 47 must be printed at some point before page number 53. 47 doesn't necessarily need to be immediately before 53. Other pages are allowed to be in between them. So the second section specifies the page number of each update. Because most safety manuals are different, the pages needed in the updates are different too. So the first update 75, 47, 61, 53, 29 means that the update consists of page number 75, 47, 61, 53 and 29. To get the printers going as soon as possible, start by identifying which updates are already in the right order. Yeah. So they explain here that in the above example, the first update is 47, 61, 53, 29 is in the right order. So 75 is correctly first because there are rules that put each other page after it. So it's 75, 47, 75, 61, 75, 53, and 75, 29. 47 is correctly second because 75 must be before it. Yeah, and so on, so on. Because the first update does not include some page numbers, the ordering rules involve those missing page numbers. The ordering rules involving those missing page numbers are ignored. Yeah. Okay. So this is a sorting problem, and for this example data, what we need to do in the end here is that we need to find the middle page number of each update being printed, but only for the correctly ordered updates. So for the correctly ordered updates, we are going to get the middle page number. So that's, yeah. And for all those numbers, we're going to sum them up, and they should give us 143 in the end for this example data. So let's look at this code for day 5 then. So as I previously have already solved this, of course, I already have that code written, but so to save some time for this video, I will not write all that code again. I will just copy it into this Scratchpad project that I have. Then I can explain a little bit what it does instead. So So first we bring in the parsing logic for the input. But we are not going to do the real input. We're going to go with the example input. So just briefly, first we split this input into two sections by splitting it by a double new line. If we look at the input again, we see that there is a double new line in between those sections. So this is the rule section, this is the update section. So yeah, so the rule section and update section, of course. Then we are going to put them into something more usable. So the rule section we will be putting in a list of tuples, split it by the pipe character. And the update will be a list of int, split it by the comma character. So then we need some kind of we need a method that we can use to determine if it is in the correct order or not. So this takes in that takes in one update and all the rules. So we cannot just we put it in a put the index and their positions in a dictionary. Then we validate according to the rules if it is in this so if the position contains x and contains y and the position x is greater than position y, then it's not in correct order. Otherwise, and if we pass all these through, we're gonna return a correct order. And so obviously it's just a matter of looping through them, sum it up, and then we will have our hopefully we will have our 143. Yes, so that's the answer for part 1. So let's go back. So part 2 of this problem, I mean, as I solved this puzzle, I got a feeling actually that part 2 would be some kind of opposite to part 1, and it turned out to be correct. So while the elves get to work printing the correctly ordered updates, you have a little time to fix the rest of them. So for each of the incorrectly ordered updates, use the page ordering rules to put the page's number in the right order. For the above example, here are the 3 incorrectly ordered updates and their correct orderings. After taking only the incorrectly ordered updates and ordered them correctly, their middle page numbers are 47, 29, and 47. Adding these together produces 1, 2, 3. So that should be the answer for part 2 for the example data. So for part 2 here, I was very fortunate actually to have already a predefined topological sort function. So I will just my idea is that I will bring in that code. We will run it and just check that we get the result we get, and at the end of the video I can actually explain a little bit more about that topological sort function, how it works. So for part 2, it's mainly that we loop through the same updates, but we use the same method as in part 1, but we check those that are not in the correct order. And then we do a sort. We sort them using our topological sort, using those rules. As I already have that method, but I will go through that method in a more in-depth way at the end of this video. And we do the same thing. We split it. We take the middle index, and we add them up. In the end, we sum it up, and we get our part 2 answer. So let's just validate that we have 1 through 3. Yeah. So part 2 is 123. So that will give us the day 5 answer. So let's check this topological sort method. So I will switch over, because I have written a unit test for this, because this topological sort, I've had that since I think well, it was a couple of years ago. I used that for another AOC problem. So I have this little AOC toolbox library where I've collected different types of helper methods and extension methods and whatnot. So but I thought when I did this, I thought that maybe this is a good way to actually illustrate how this works. So here we call them nodes and edges. So the nodes in this case would be, in our day 5 example, would be our update, and the edges will be our rules. So these are actually the rules from that day 5 test, day 5 example input. So I just wrote this test today, so just so I could explain a little bit about it. So what we are going to do is that we are going to sort this using this topological sort. So let's run our test here. So let's check this code out. Yeah. So this topological sort, it first creates a graph and degree dictionary. So and first it initializes that. What it actually checks here is how many times each of the nodes appear in these edges, or exactly what if the edges, if the node contains both the x and the y of the edges, then we kind of fill this graph. We add the left edge, or the right edge, actually the right edge of that to that graph. We also increase the degree. So if you move past this, I can show you. So now we have our input. We have 53, 75, 97, 47, and 61. You can see that 53 now has 0. So this is how many times it found them in that. For the degrees, we have 53 at 4. We have, so the sorting algorithm actually takes in those degrees. So we will actually sort them according to the degrees. So we're using that. It's using a queue for this. So we begin by dequeuing the first node, which in this case would be 97, because that had we're going to start by the lowest degree, and then we are going to decrease. So in this case, if we're looking at either the neighbor, you find the neighbor 61. So in 61 has 3, so now we decrease that to, so now it has 2. What we want to find is if any neighbor reaches 0, we will enqueue that as the next thing to sort, to add to the sorted output. So we're going to loop through. We're going to find, I think it will be 75, yes. So 75 will be the next according to those rules. So this is how it works. It kind of decreases the degrees for the other neighboring nodes in the graph, and in the end we have a sorted output, which is like 97, 75, 47, 61, and 53 at the end. And I just my assert method to assert those conditions. So that's a little bit more in depth of how this topological sort method works. So I hope you like this video, and I hope you can hope you also subscribe to my channel and comment if you like this content. Right now I cannot add links to my YouTube videos because YouTube I need to be verified for some reason on YouTube. So, but if you go to my channel's homepage, you will find the link to my GitHub, and there I have all this code in my GitHub. So if you want to check it out yourself, you can go to my GitHub. Okay, so that's all for today. So see you tomorrow.